be demonstrating on how to use R. So first we need to generate the random data set. I'll be running this, and then from here I will write true, run, and oops, sorry, data .csv, So this is the auto-generated data. Let's have a look at the linear relationship among two continuous variable and look at the graph. So I will plot data score. I'll use score and time 2. Okay, so this is what we have so far. Smooth data score data time 2. So this is the linear the graph. Let me just identify data as x as score, y as right. So then from here we can create a scatter plot. YLab. Okay, so let's look at the line and see if it data color, let's make it blue. Okay, so this is the relationship between score and time 2. It seems to have an invert relationship. So from here, let's run the test, t-test. So for t-test, there's a few assumptions that needs to be met, or there's particularly for different types of t-tests. So first of all, let's check for the normality. So let me have a look at, I'm going to use the same data. Okay. Time 2. Okay, so this is how it looks visually. Let's run the Shapiro normality test to see if it is indeed normally distributed. Let me run for time 2. Yeah, they are both normally distributed. So the assumptions of them being normally distributed is correct. So let me briefly explain. So Shapiro-Wilk normality test checks for the normal distribution of a data set. It's to compare whether or not they are normally distributed. So a p-value of 0.05, anything below that would indicate a non-normal distribution. But as you can see, for both score and time 2, they are both normally distributed. So from here, that's one assumption that is met. The second assumption is equal variances assumption. So we can run it using this variance test. So data using score and data using time 2. So it seems like the p-value is less than 0.05, that means it is statistically significant, indicating that the two sample, they do not have equal variances. Sorry, the two data do not have the same or equal variances. Okay, so in this case, normal distribution is met, but the equal variance assumption is not met. Therefore, we need to run a Welch t-test that does not assume an equal variance between these two data sets. Score and data time 2. Right. So the Welch t-sample t-test indicates a p-value of 1.052 to the power of -9. This means that this is a lot lower than 0.05. Therefore, the t-test is statistically significant. Okay, this means that these two samples, these two data sets, score and time 2, may be responsible for one another in terms of changing their responses. So now is to test between any a correlation test. So we shall now so now we will be doing so now we will do a correlation test. So this is between any variables. We need to run a correlation. So I'm going to use the same thing as just now, which is score and time 2. So they were both equally distributed just now. Therefore, I will skip the Shapiro-Wilk normality test. The assumptions for a correlation is that it is normally distributed. Therefore, I will be using, I will run it again actually just to show. Shapiro.test, data score. Again, it is normally distributed. Test data time 2. It is normally distributed. So in this case, assumption is met that it is normally distributed. Therefore, I will be running a parametric correlation test, which is the Pearson. So I will be running test data score, data time 2. Method Pearson. Right? So the p-value is 0.1551. So this means that it is not statistically significant. Therefore, there is no relation between these two data. So from here, use a regression test between variables. So I will be running between any variables. Okay, so Shapiro test, just again, I will be using score and time 2, but let me try time 3 actually. Time 3. Okay, same thing. So let's try and see if we can get any model. Time 3. Okay, so this is, so the p-value is 0.2112, indicating that it is not significant, statistically significant between score and time 3. There is no regression. Conduct an ANOVA Kruskal-Wallis or a Kruskal-Wallis test using any 3 variables. So the first, what are the assumptions met? We're using parametric or non-parametric. So ANOVA is a parametric test, whereas Kruskal-Wallis is a non-parametric test. The difference between parametric and non-parametric is whether or not parametric assumes a normal distributions on the data set, whereas non-parametric test has no such assumption. Okay, so for now I will create a subset. So it will be, I'll use ethnicity, Chinese, Indian, subset, data, ethnicity, Indian, set, data, ethnicity, Malay. So I will be running the normality test first to see whether or not it is actually normally distributed. Shapiro.test Malay time 2. So the p-value for Malay time against time 2 is statistically significant, meaning that it is not normally distributed. Let me try for the rest. Sorry, Shapiro.test. Normally distributed. Shapiro.test. Indian time 2. Okay, so for Indian and Chinese against time, it is normally distributed except for the Malays. Therefore, ANOVA cannot be used. We have to use Kruskal-Wallis test. Kruskal.test. Okay, so time 2, ethnicity, data is equal to data. Oh, Kruskal test time 2. Ethnicity, data is equal to data. Right. So the Kruskal test ethnicity by time, it is, the p-value is 0.005, meaning that it is significant. So now we'll be showing 2 graphs using G&J plot. So let's see if I can wait, first I need to log in. Alright, so ggplot. Function of -3. Geo function of so this is a graph, a normal distribution graph that I skim up, and another one would be can do the same with inverted -2 2 plus geo function of fun So this is two graphs showing using a ggplot function.